Hey there, welcome back. Today we're going to continue working on the BorgWarner 4419 transfer case controller. Basically, we're just replacing the factory OEM controller for the transfer case with our own microcontroller and logic. Today I want to talk about the code. There are a few things that we're going to look at. Most of it's really easy. You may recall that shifting the transfer case is simply driving a DC motor, either in the clockwise or counterclockwise direction, to get it to shift into a different gear. Nicely, Meadow Foundation, the core has a bidirectional DC motor that takes into it two digital outputs. We can turn those on or off. Basically, they are the outputs that go to the relays. And then this abstracts that into a class that is this motor that either has a clockwise, counterclockwise, or stop method on it. Really, really simple. So basically what we've done here is we have an A and a B. Those are the two relays. We have output ports for each. On 0 and 1, we initialize them to both off, so the transfer case is not going to be moving when we start it up. And then we create the instance of the motor. Then you can see here, driving the motor is as simple as this. We turn it clockwise for a second, then wait a little while, then turn it counterclockwise for a while, then stop and wait a while. Really simple. This is what you see in the sample that I showed at the end of the last video, where all I was doing was exercising the motor to make sure that the circuitry and the wiring worked. In the last video, I built this surrogate for the transfer case because I don't have one of the transfer cases lying around, and even if I did, having it in the office would be a bit of a challenge. So we've got the motor here, drives this rack, and it moves over and crosses these switches. If you take a look at the schematic here, you can see that it's got these switches inside the transfer case. And that's what these limit switches represent. So basically, they're just closed contacts. I've got 5 volts coming from the microcontroller up into each one of these, and then when it connects one of them, the 5 volts goes back to an input on the microcontroller. So this wiring harness comes over, and we've got 2 plugs. This is the 5 volt source from the microcontroller, and this goes back to the switches. And so over here, this is where the switches come to digital inputs, and this is the 5 volt source. This might be a little bit noisy on these contact closures, but nicely I can debounce that in software, so I don't need to add any circuitry for it. The next task is to integrate those switches into the software. What I've done is I've just created a class called the BorgWarner 4419. We pass into it that bidirectional motor, and then are 4 interrupt ports that are those 4 switches. Then we're going to look for interrupts or change events on those switches, and those simply set our current gear. So when the high 2 switch is closed, we set our current gear to high 2 or 2-wheel drive high. And same thing for the others. We've got a neutral as well. We're never going to shift into neutral, but we need to know where its position is. These positions are a simple enumeration, so it's either I don't know. Unknown is actually when you start up, you don't know what gear you're in, but also if you're between gears. So if it's in the process of shifting between gears, we call that also unknown. And that'll make sense here in just a second. So when we want to shift, we can do a few different things. The easiest ones are to shift up or shift down. So up, if we take a look at this position, up is simply higher in this position enumeration. So from low 4 to neutral or neutral to high, basically it's turning in one direction of that motor. So you could think of shift up as going clockwise with the motor to get us to a different gear. Down is counterclockwise with the motor to a different gear. So we're going to take a look at shift up. The first thing it does is it makes sure if we're already at the far range, so we're already in the highest gear, we don't want to continue, we don't want to do anything, so it just exits out. Otherwise, it remembers what gear we're in, and then it starts the motor turning. And while we're either in that certain gear or we're in an unknown, so between gears, so if we're in that unknown state, it's just going to continue to wait. And every 10 milliseconds, it checks, are we in the gear that we started in? So when we very first start out, because there's some travel where it will continue to keep that switch closed, we want to continue driving. Or if we're between gears, continue driving. Once it is no longer in unknown or the existing gear, so basically it has changed gears, it then stops the motor. Shift down is the exact same thing, except it turns the motor clockwise instead of counterclockwise. So then we can take that logic and we can do things like shift to. So this is going from whatever position we're currently in to a given position. So it simply checks to see, is the desired position higher or lower than where we are? And then it uses that shift up or shift down method that we just looked at to shift those gears. Before we start a shift to, though, we do verify our current gear. The reason being that current gear is set on interrupt, but this is a poll that goes out and looks at all the switches and decides, are we actually in the gear that we think we are based on interrupts? And all that does is it looks at the state of the switches to determine which one we're in. So it's extremely simple. So if we take a look at an example of how this is used, we create the BorgWarner 4419, passing in the motor, which used those digital output ports on 0 and 1. And for inputs, we just use the inputs on the Meadow, D10 through 13. It starts out and it feeds, and this basically is only for testing for this test harness. It feeds it to the lowest position, and once it has done that, when it's in low 4, it then shifts all the way to high 2. So it waits until it is shifted, and then it goes back into low 4. So it just goes back and forth between high and low. It is not stopping at any of the gears in between. We've now handled driving the motor on the transfer case, which shifts it. We've handled the switches that tell us what position it's in. Next, we need to handle the user selecting a gear. So how does a user select what gear they're going to be in? There are a few different ways you could do this. Switches, toggles, whatever. But this one, the customer wants to actually use a factory switch. And if you take a look at the picture of the factory switch up here, we've got 3 gears, 4 high, 4 low, and 2 high. If we take a look at the schematic that they provided to me, this one has an auto, which this switch does not have, but otherwise it looks like it works the same. So we have a switch that when we rotate, it actually goes through resistors here. Now, the fun of this is it doesn't tell us what the resistance on any of these are, but they all come back on a single wire coming back. So really what we have is a discrete potentiometer. So we have a potentiometer that has specific settings, so 3 specific states, and what we're going to do is drive power to that and then have it go to ground on the other end. And we're basically going to build a voltage divider and take a look at the output of that voltage divider to see what gear we're in. Now the fun here is an automotive system does not have a constant voltage. So the 12 volts in, we call it 12 volts. It's, again, not 12 volts. It's usually around 14.5, but it isn't the same all the time. What we really need is we need a constant voltage so that the voltage divider output is always going to be the same for a given resistance. Therein lies the challenge. One of my coworkers suggested a novel approach to this. It is to use an LM317 and provide a constant current out to it. If we've got a constant current, Ohm's law will tell us that Constant current with a constant resistance, that resistance being the switch, has to give us a constant voltage. So it doesn't matter what the input of this system is. If we've got it regulated to a constant current going through a constant resistor, our output voltage from that voltage divider is going to be constant. So that's perfect for what we want to do. So I took a look. We've got this LM317, and by wiring it up like this with a constant resistor here, and instead of an LED output, this will be our switch resistor, and then we'll measure right here at this bend where it says L1. That'll be our output to our microcontroller. We can measure that. So it doesn't matter what the input is over here for the voltage of the overall system. The LM317 is going to give us a constant voltage here because we have a constant resistor here and here. If you're interested in the math on how this works, let's just go over it really quick. Basically, we've got our LM317 here, and we've got our input voltage, and this is going to be, anywhere from probably 10 to, let's say, 18. It shouldn't get that high, but we'll just put that in there. And then we're going to have a decoupling cap here. This isn't terribly important. What is important is here we've got a fixed resistor, and this is what drives the amount of current that we get down here. Now, I've already done some of the math, and so I know if I put a 220 ohm here, so the calculation for that is really simple. It's 1.25 divided by this R gives us our I. So 1.25 divided by 220 is 0.00568 amps. And so that is our current here. Now we've got some long wire going over to the switch, and then that goes to ground. And really this switch we've said is like a potentiometer. So here's our switch. So the thing to figure out is what is the voltage measured right here. So we're going to have our voltage come out. Here. The question is, what is the voltage out here? And we want it to be, in the range of 0 to 3.3 because that is what we can measure. If it's a little bit higher than this, we can go all the way up to 5 volts because we're 5 volt tolerant, but we can't detect any number between 3 and 5. So we know that this switch has possible values of 130, 270, and 620 based on a video that the customer took for me showing this. Now, I don't have a 130, 270, or 620, just a resistor sitting on the shelf, but I do have a 150 and I have a 680. So we're somewhere in this range, right? So if we do the math for this and we put our R here and our output, not amps, but volts. So V equals IR. So basically our voltage is this I, 0.00568 times our resistor here. So if we've got, say, 130, this should give us 0.74. The 270 will give us 1.53. And 620 will give us 3.52. Now this again is a little bit above 3.3, but it's within our safety margin of 5 volts. And we only need to know if it's at this, or this. So if we get 3.3 volts, or max saturation on that input, we know it is in this gear. Now, I'm going to hook up a bench power supply to this circuit just to verify. On paper, this is all correct, but we want to make sure before we hook it to a microcontroller and let the magic smoke out that everything is right. So we'll try it with a 150, which I have, and a 680. In theory, this should give us 0.85, and this should give us 3.86. So let's try this on the bench and verify that this circuit works and gets us these two outputs. It's a little cluttered here, but I've put the circuit together. Here's the regulator. Here's that resistor, the 220, and then I have a 150. This simulates our switch. I'm going to feed it voltage here. Right now we're at 11.5, 11.6. Now in theory this should give us 0.85 volts out. So that looks pretty good. This is only giving us 1 decimal place. And now the nice thing we need to check is what happens if the voltage in the system goes up. You can see even at 16.5, even at 19 volts, we're still only getting that 0.85 out, which is exactly what we want. It's important to point out at this point that I am not an electrical engineer. I have not taken any EE classes. I really don't have any specific formal training, just putting things together. You know, I've got a basic physics background, but that's it. When I soldered this circuit up, everything seemed to work pretty well. Tested it out, everything shifted just fine. I actually shipped a version to the customer. He hooked it up. Seemed to be working just fine for him as well for about 3 or 4 hours. Then it started to make some noise. He said it sounded like it was kind of screaming. And then it, made some smoke and then quit working altogether. The question I had is what could possibly have happened? So I put it together again on my desktop and was testing things out. And I noticed that if I didn't have any switch connected at all, it got really hot, really fast, and cooked one for me as well. So I decided, let's put this into a simulator and see what happens. The circuit here is a simulation of what we've got going on. There's a 130, a 270, and a 340. This 50K ohm, this is the microcontroller's ADC. And so if you simulate this, and I had to add a few switches in order to simulate that 3-position rheostat, but this is effectively what we have. A 340 ohm gives us 192 volts. Looks fine. A 270 gives us 1.53 volts. If you go back and look at the math, this exactly matches the math that we did. And then if we run it through the 130 ohm, we get 736 millivolts. So all of that looks really good. So I was still confused as to why this would be happening. Well, it turns out that there is a situation that I'm not accounting for here. That 3-position switch, when you're switching it, there is a moment when this switch is not closed to anything. So there is no connection over here on this right side to ground. So effectively, it opens this loop, just like this. And look what happens here. It says 284 volts. Obviously, it's not going to get that high with a 12 volt or, a 15 volt source, but it certainly is going to get a whole lot higher than the 5 volt maximum we want. I suspect it's running all the way up to battery voltage when you make this connection. And running, 12 or 15 volts into a 5 volt input causes it to get real hot and the smoke to come out. I ended up going back through and reworking this with a bit more complex of a circuit, but a much safer circuit. So we still have our resistors over here. So when everything is working, we have this closed here, but when it's not, I have a bypass here that allows current to go through to ground. There's also another series resistor here that helps limit the current, and there is a Schottky diode here that actually dumps excess voltage back to the 3.3 rail. So in all cases, you can see here, this is only at 2.63 volts, even when nothing is connected. So this is what I ended up building the second time around and sending this over to them. They've had this installed on a vehicle for, I think, almost 2 weeks now. Well over a week anyway, and I haven't heard any complaints. I also built the same thing here, tested it here, let it run with nothing connected over the weekend, and I didn't have any problems. In the end, what I ended up with is this. This section over here on the left is that circuit. So here's that Schottky diode that pulls up to 3.3. Here's the LM317 and those resistors. While I was in here, I also did a few other things. I put in series resistors to these switches that go to the transfer case, and I also put in 10K pull downs. Originally, I had these as pulled down through the microcontroller. The problem with that is when it powers up for the short period of time before it initializes these, they're probably floating, and I didn't want 5 volts running out through the switches and then back in through it with no resistance at all. So I added those in. And then here's the circuitry for these transistors and the relays. Again, links to the repository that has this schematic in it is down in the description. I'll also put a link up in the upper right if I haven't already put it. And this is what it looks like physically. This is actually the original one that I sent that burnt up. I've repaired it and put it back together with a new meadow in it, and this one also tested out just fine. I've got the 2 relays that we're using for driving the motor, all of the circuitry, and this is the 5 volt supply. It's actually an adjustable supply, but this takes from the vehicle voltage down to the 5. So here are the transistors. This is the circuitry that I added in order to limit that voltage, and then I added a fair bit underneath as well. So here's that diode. Here are those pull downs that I was talking about. Here are some other diodes over here. The moral of the story here is if you come from a software background and you're building hardware, expect for things to go sideways on you. Expect to blow things up, burn things up. Test, and retest, especially with a meter, and don't get discouraged. There's always a reason why it went bad, and you just have to dig in and figure out what it is. If you've got any comments, feel free to leave them down below. Any questions? All of the schematics for this and the code for the entire solution is open source. It is over in the repository. I've got a link down in the description. I will be adding other automotive controls over time as I build them up. If you have anything that you would like to see, or if you want to help out, feel free to contact me. Thanks for watching.